Hello, this is Ron, and we're going to be talking about some more thermodynamics today. The title of today's video is The Different Forms of Energy. We will look at something that we call total energy, something that we call specific energy, and then the rate of energy, and I think we also may know a different name for that. After we get done looking at these different kinds, we'll rewrite the first law of thermo for each kind. So total energy is the form that we're most familiar with. We use the capital letters to dictate or to show total energy, and so I have potential energy, and then the equation for potential energy would be mgh. So we're doing total energy here. And I think we're all pretty familiar with the units of total energy, joules, BTUs, foot-pounds. So let me get my little symbol on here. Let's go ahead and use BTUs. Now, I would have the same thing with kinetic energy, internal energy, work, and heat transfer. Let me just go ahead and make the list. Kinetic energy, internal energy, big U, heat transfer, and work, all capital letters. So then if we want to say, well, what's the big deal here? Well, let's take a look at another form of energy. And we'll talk about specific energy. Now, specific energy is simply total energy per unit mass, or divided by mass. And for specific energy, we use lowercase letters. So I would say little p, little e, and well, what's mgh divided by m? Oh, it's just gh. And kinetic energy would just be v squared over 2. And then for internal energy, we really don't have an equation for that yet, though we'll get a couple, and for heat transfer and for work. But what would the units be? Well, what happens when you take a BTU and you divide it by a pound mass? Real original here, we're going to get BTUs per pound mass. Now, why would we do this? Well, in most systems that have something flowing, we care less about what the total energy is in that flowing system and care more about how much energy does each unit have. So how much energy does each pound have, or each kilogram, or something like that. So it is useful. In fact, we'll get to the steam tables before too long, and in the steam tables, all of the energies are specific energies. So to finish up here, we have a little k, little e, a little u, a little q, and a little w. Let's go to another color. And talk about rate. The rate at which energy is done. Well, the ones that we do most commonly with rate are work and heat transfer. And rate means, or rate is signified by a dot. Now, sometimes in calculus, you will use a dot when you take the derivative with respect to time. Well, another way of saying the derivative with respect to time is rate. And so the units are BTUs. Oops, that's not a very good U. Let's fix that. BTU divided by, most common we'll see in thermo is BTU per hour, but there are many, many, many other ways of talking about the rate of energy. First of all, another word for it is power. And with W dot, we would call that mechanical power. With Q dot, we would call that thermal power, also very commonly called the rate of heat transfer. So when we start talking about power, well, then we've got horsepower is a unit, foot-pounds per second are a unit, and of course some other units. If we talk metric, we've got joules per second, and we all know that is a watt. So lots of units of power. Now there really isn't a rate of potential energy. So what we do when we get it into the equation to have all of the first law is we'll take the mass flow rate, m dot, and multiply that times the specific potential energy or the specific kinetic energy or the specific internal energy. So as a quick little review here, we've got total energy, capital letters, it's how much energy a pound of something, or 25 pounds, or if you wanted to talk about how much energy your body has, you would talk about total energy. You want to talk about how many calories the food that you just ate has, you're talking total energies, calories, BTUs, joules, kilojoules. But in engineering, we quite often use these other two, the specific energy, how much energy does each unit of mass have, and the rate of energy, or the power. When you think about selling electricity, we sell power, and then sometimes we give it units of total energy and multiply the power times time. So, as I said, we will go ahead and now take a look at the first law in each of these ways. So we have a new page here, first law of thermo, total. So in total, we'd take the total potential energy. Oops, get the right tool here. We'd have the initial capital potential energy plus the initial kinetic energy. That's pretty ugly. There, I fixed it. Plus the initial total internal energy, plus then any heat that we transfer in, minus any heat we transfer out, plus any work that's done on, minus any work that we do by, and will equal the final potential energy plus final kinetic energy plus final internal energy. So this is the energy balance. The units in every term are the same, total energy, joules or BTUs or calories or whatever. Start with how much energy does something have, how much energy does it have stored, and we talk about stored energy as these three, and we put some in, take some out, put some in, take some out, and how much energy do we have at the end. Now I'm going to hit pause and rewrite this in little letters so as to not waste our time together. So here we have the first law in specific terms. I'll give you a few seconds to write that down. But it's really the same equation It's just that we've divided everything by mass. And again, the reason we're doing this is there will be certain instances when we apply the first law that it's more convenient and makes more sense to use total energy. There are certain instances when it'll make more sense to use specific energy. And then with rate, what we do is we say, well, we have something flowing. And when we have something flowing, it has mass flow rate. And it flows into a system. Let me just draw a little system here. What if I have a box? And that box has some water flowing in, and it has some water flowing out. And while in the box, we put some energy in, or we take some energy out. Maybe it's a boiler, or maybe it's a turbine. So we could do any of those things of putting energy in, and with rate we would say, well, that's Q dot in. Or we could take some energy out. Maybe it's warmer than its surroundings, so heat is being transferred out. Q dot out. And there's certain ways we could put work on or do work by. So the screen up here a little bit, but we've got any system that has something flowing in and something flowing out. Energy flows in with that mass that flows in, and so we take what's the mass flow rate flowing in, and then what kind of energy does it have when it flows in? Does it have any specific potential energy, any specific kinetic energy, or any specific internal energy? That's the kind of energy that's coming in with the mass. And while it's in the system, well, we can put energy in, Q dot in, mix it up here a little bit, or W dot on, that would be putting energy in. Taking energy out, I'm going to move down here with my equation, minus any Q dot out, minus any W dot by. So the mass comes in, it's got energy. We put some in, we take some out. And then what leaves? Well, we've got mass flow rate out. Oops, that's a times. So times the potential energy that's leaving, kinetic energy leaving, and internal energy leaving. Now, this is a special way of writing the rate equation. We have made an assumption here, and the assumption is steady state, and we'll have more conversations about steady state either in other videos or in class. But this right here is perhaps by far the most common way in industrial applications that we will use the first law. It is in a rate term. Well, let's go ahead and take a quick look at those units. If we had mass flow rate coming in and it had pounds mass per hour, and any of those little energies there, they would be in BTUs per pound mass. Pounds mass cancel out, and so all of these terms are BTUs per hour, BTUs per hour. And then the rate of heat transfer, or the mechanical work being done, BTUs per hour. So they're good units. All right, that's the end of this video. Have a nice evening, day, whatever it is, wherever you are.